Now let's just talk about the theorem which is related with tangent to a circle. It says that tangent at any point of a circle is perpendicular to the radius through the point of contact. So let's just prove this theorem. First of all, let us suppose if I'm just drawing this particular theorem into a figure. So let us suppose if I'm just taking this figure, and let's just start with the given conditions. Let us suppose if I am just taking the given conditions that we have a circle with the center O and radius OP intersecting the tangent xy at the point P. So let us suppose if I'm just taking the center as nothing but this particular point P. Now let's just talk about the construction over here. I'm just doing a little bit of construction over here, that take any point Q on xy other than P and join OQ. So let us suppose if I'm just taking any particular point Q over here, let us suppose if I'm taking Q on xy and I'm just joining this OQ. Remember, this Q point is other than P. This is other than P. So I'm just joining this OQ in this particular manner. Now let's just start with what we have to prove. We have to prove that the OP is nothing but perpendicular to xy. Let's just start the proof of this particular theorem. So first of all, since you can see that Q is actually lying on OQ. Q is lying on xy outside the circle. So as you can see, the xy means this Q is actually lying outside the circle, and it is lying on the xy, and it definitely cannot lie inside the circle, because if it lies inside the circle, then this xy would nothing be a secant. So since Q is lying on xy outside the circle, as you can see, this is lying outside the circle. It cannot lie inside the circle, because if it would lie inside the circle on xy, then this xy would become a secant, then it won't be a tangent at all. So we can say, since Q is lying on xy outside the circle, then we can see that OQ distance is larger than the radius. You can see all by yourself, then this distance is definitely larger than the OQ, then the OP, that is OQ is nothing but greater than OP, and similarly the distances of all the points lying on xy from O is greater than the OP distance. Hence, OP is the shortest distance among all, and since if OP is the shortest distance among all the distances of the points that are lying on the xy line, it implies that OP is nothing but perpendicular to the xy. Hence it implies that OP is nothing but perpendicular to xy, because if you can take any particular point on this particular tangent, then those distances or those points distances from this point O will definitely be greater than this particular distance that is nothing but OP. So OP is actually the shortest among all the distances. So it implies that OB is nothing but perpendicular to XY. So this is nothing but the proof of this particular theorem, that the tangent at any point of the circle is always perpendicular to the radius through the point of contact. So since definitely this is nothing but the point of contact, so hence this is nothing but perpendicular, that is an angle of 90 degree. So let's just see the remarks that are related with the previous theorem. So the very first remark would be like, at any point on a circle there can be only one and only one tangent. So always remember, if we are just talking about any particular point on a circle, then for that particular point there is only one and one tangent, that's all. Now the second remark says that the line containing the radius through the point of contact is also sometimes called as the normal to the circle at a point. So this is really a very important concept, that sometimes the line that is containing the radius through the point of contact is many a times also called as the normal to the circle at a point. So this is all about the remarks that are related with the theorem.